It's an honor to introduce the other invited speaker, which is Professor Subhash Risbud. Is a distinguished professor emeritus of material science and engineering at the University of California.
So, we are working on a joint project with Brian Leaners of Homerun Resources, who's based in Vancouver, Canada, but we are at UC Davis, and it's a collaboration that's been funded by him for about 2 years. And the purpose, of course, is to make fused silica optical glass from a large resource of raw material called quartz sand, which is available. And we are doing a variety of what we consider rapid heating processes to do this. So the company that's funding us is Homerun Resources, and he's our collaborator, supplier of our quartz sand, and also the support from my graduate students, 2 of them. So I will talk mostly of the work that we've done in this focused area. Because as most of us know in the field of optics and photonics, and I've been at this since my days at Berkeley and subsequently in the Optical Sciences Center at the University of Arizona in Tucson, that fused silica and glasses can be used as a primary medium for data storage, durability, stability, and all of these applications, of course, require a high purity level of silica sand, which we get from a Homerun, and then through a laser process we purify it, which I'll talk about later in this talk. But the applications right now that we are working on are to develop a process to rapidly produce silica glass. And glass is my favorite subject for years, since my days with Dick Fulrath at Berkeley and subsequently at Illinois and Arizona, where we worked a lot with growing quantum dots in glasses, and also silicate glasses and silica particularly. So the 3 methods I want to talk about, which we are researching, is to reduce the amount of time it takes significantly to make the fused silica glass from the raw sand, which is basically clumps of raw material from the earth. And the 3 methods we have tried, and not all of them have been finalized to perfection at all. One of them is flash Joule heating, and the second one is arc welding, and finally microwave heating. So I will talk about all of these methods a little bit. Flash Joule heating is a highly efficient energy-saving technique used for rapid making of many materials. But the problem with fused silica, of course, is normally it takes, because of the high viscosity, as most of you know, takes hours and hours to make it. So we want to reduce that time to minutes if we can, or even smaller. And the method of flash Joule heating leverages high electric current to generate localized intense heat and passes the energy on. So it's a lot better than traditional furnace heating. The problem with silica, of course, being an insulator, that is you need to surround it with something that will actually conduct. So, we've done a methodology that shows, first of all, we use the sand by 3 different methods, as I said, and then I added a 4th one to this list, which we have been quite often doing for many, many years at Davis, called smart plasma sintering, which of course has spread all over the world now. So we started this in the 1990s timeframe through a machine donated to us from Japan called Dr. Sinter, which basically says you can convert a powder to a dense disk in minutes rather than hours. And microwave melting and freezing is something newer, which we're just starting. Arc melting, of course, I just mentioned, where you put rock pieces in, and I'll show you some limited, early experiments we've done with that. And then, of course, flash Joule heating. So those are the 4 methods I want to talk about, the focused goal being to make fused silica glass. So our equipment for the flash Joule heating is a Joule heating system equipped with a stainless steel chamber, a platform delivering ultra-fast thermal pulses with a tunable voltage and all of this. But critical to it is the conductive medium. So because silica is insulating, we developed a method in which we put 2 tubes, one inside with the silica in it, and the outside one contains graphite or something which can conduct. So that's kind of the start of the process. And here's what we kind of physically see when that happens. So This is the flash tool heating. The middle of it, you see turning glowing orange and yellow, is where the melting is happening. And then the glass that comes out of it is the result. And usually, in about 5 minutes at the most, the temperature reaches fairly high temperatures, as I mentioned. And so I'll tell you what that is. Here's a closer look at it. And then if I go on to the next one, so the success of our process, at least in the limited way we've done so far, my friend Kokoro is doing his PhD thesis on this. He's incorporating a tube-in-tube configuration in which the outer tube contains the conductive substrate, which is either graphite or something similar, and then the higher temperature from the graphite then transmits to the inner tube, which contains the silica. So critical to the good results that we got is that when the peak temperature, which we estimate to be about 2000 centigrade, even though it's for a short time, which is well above the melting point of silica, as you must know, and given that, the viscosity of the silicate melt being what it is, we thought it was a promising result that we could reach a temperature like that, even though for a short period of time. So that gave us a good piece of, initial glass thing. The next technique that we are hoping for much better success to is arc welding for making fused silica glass quickly. And that process, as many of you must know, involves a copper conductor inside an arc welder. And because copper is, of course, not melting at high temperatures, we put lumps of rocks of silica in there. And we have just started this experiment. And the copper is, of course, cooled during the arc welding process. And what we should be getting is something like this, where you see a flash of a flame in the arc welder, which hopefully melts the lumps and rocks of silica. The copper outside, of course, doesn't melt. It's water cooled, obviously, and it's short term. It's very short time frames, and the success of it is just starting to be seen. And this is the kind of initial, the copper powder he's holding in his hand, obviously is pretty big, but the stuff inside is kind of partially melted, partially not. So we're just starting to do these experiments, and hopefully we'll get more successful results. Our ultimate goal is to get a glass disc of some sort, which is transparent and clear. And then in the previous studies that Denise Kroll and I did many years ago, we did some structural studies of putting exposures of laser to this glassy silica, fused silica, and observe the local coordination structural changes through NMR and Raman spectroscopy and stuff like that, which is one of my other interests, and we'll talk about that some other time. But here is making of the glass. That's my first goal and one that I want to, keep going. The other technique, which we have been very happy with for a lot of reasons, and these are equipment that was, again, from Sumitomo Coal and Mining model, the Dr. Sinter, which is basically a machine which utilizes a graphite die or any other die you may have, and you put powder inside it in this area that I have shown here. And then in the area that you squeeze the sample, you essentially get a dense disk from powder to disk. And the sintering temperature can vary. I mean, you could be as low as 200-300. But key to this process is not so much the pressing. Hot pressing does that too, so does hipping and all the other techniques. But here, the beauty of the technique is that the first step at room temperature essentially is an electrical pulse. So when the powder goes into the graphite die, you apply an electric pulse that's an on-off type of a situation, and it goes on for maybe just a minute or two. So the powder then first sees this on-off electric pulse for a short time, and then you heat this whole thing up to temperature. And often the graphite die is surrounded by graphoil sheet, so it's pretty much protected from any other exposure. You can put this under vacuum condition, or put argon or helium or other gases in it if you like. So that's kind of the typical arrangement for it. The Dr. Sinter machine uses a graphite die. The diameter of the die can be chosen from as little as a millimeter, or no, a centimeter, sorry, in diameter, to as much as couple of inches diameter, and doesn't have to be cylindrical either. We have square dies of all sorts. So the key step, of course, is the first electrical pulse. And then the temperature of scaled up in the way you design it. And it's an automated machine, so it can go up and down in temperature as you choose. The cooling rate is not very fast. I mean, you just shut the furnace off essentially, and so you're not in any sense of the word quenching anything. But it does raise the temperature up to as high as 2100 or even higher. And we've tried using carbides and borides in here to sinter as well as of course, the silicious materials. And so the next thing I want to talk to you about is probably more related to laser processing, which is one of my grad students doing this, because the quartz sand we get from Brazil is impure, and people have used all kinds of chemical techniques of, flotation, acid pickling, scrubbing, all that, to purify the sand to higher levels of content of silica, and that's high purity is what we desire for a lot of application. So one of my students has been doing this work on basically using the quartz stone and moving it into the next stage of pickling and acid production. But instead, we took the approach that instead of doing it this way, let's try doing something else. And that was, normal steps, as you know, are the 1, 2, 3, 4 here that I'm showing, and acid pickling. But what we decided is let's try a different approach, which does not involve chemicals. So no acids, no water, no separation like that. We just take the sand, ball mill it, and then we go through the laser process, and we end up with getting pretty high purity silica sand, 99.9. And this is what we would like to use eventually for our work on melting it to fuse silica glass. So the way this system works is we set up a femtosecond laser, and then all of you familiar with this laser know that the pulse duration is only about 100 femtoseconds. And then the sample is this way, the laser beam hits it, and then it goes on, and then material ejection occurs, and here's the analysis. So if you do chemical analysis of chemically purified acid wash materials, you get something like 99.98 at best, but it's a very tedious process. And in our laser process, even at something like 2 to 4 or 5 hours, maybe 6, you get very high purity, 99.99. In 12 hours, you just about get the best samples you can get. Now, whether you need this quality of purity or not is another matter. And so we have been trying to see the temperatures reached using different laser wavelengths and playing around with, how high temperature you can get and how much time it takes to get the best purity you can get. So this is kind of another project we have ongoing. So our continuing work, as you know, many of you who are advisors for PhD students, 2 of my students are doing this, and they kind of are exploring different ways. And our continuing work now in the future will focus on better control of heating rates, pulse duration, and temperature for the laser processes, then designing conductive matrices that allow rapid heating during the flash Joule heating. And then, of course, we're scaling up to larger amounts for fused silica glass with arc welding. And more recently, we have been now playing around with trying to put it in a microwave oven and see if microwaves can melt it as long as they're surrounded by alumina and other fiber fabric around it to protect it from, from the melt. And so that's kind of our goal right now, is to continue this work and try to aim at making fused silica glass from the Homerun derived samples. So again, I want to thank Homerun for funding this work, and my grad students, Arish and Petrina, who's come to us all the way from Ghana and done good work. So we are grateful to both of them. And again, our work is focused again on fused silica optical glass of high quality that can be made in quickest amount of time. Thank you very much for listening to me, and I appreciate the invitation and giving this talk.